All right, this worksheet covers various exponential decay problems, so b will always be less than 1, and there's my b right there. It's a half, so we're cutting something in half. We're cutting aspirin in half. We're cutting 325 milligrams of aspirin in half. So my equation is amount equals 325 1/2 to the t over 15. So we have a 75-pound dog. We put aspirin in him to help him with his arthritis, and we want to find the amount A after so much time. Well, no, we know the amount A is 50, and we will figure out how much time it'll take to get from 325 to 50. So 50 goes in for the final amount. So right, 50 is equal to 325, and then half is 5/10. I'm going to change that to a decimal because it's faster to type in the calculator. And then it's t over 15. And it's really hard to see that it's t over 15, so I can zoom in here. My zoom button has disappeared. Is this the zoom button? Whoa, that's weird. The zoom button is just like gone. Oh well. So we're going to solve this by dividing over 325. I'm going to go ahead and leave that fraction. That cancels out, and I get 50 over 325 is equal to a half, and then it's t to the 1 over 15. So we need to bring the exponent down to the front. We do that by taking the log of each side. Get a different color pen here. Log, log. And then the exponent comes down to the front. That's one of our properties of exponents. So I have log of 50 over 325 is equal to t over 15 log of a half, or 0.5. I have to get t by itself, so I'm going to do two things. I'm going to divide the log over and then multiply the 15 over. So t would be equal to multiply the 15 over, so it's 15 log 50 over 325, and then I'm going to divide this log over, so log of a half, or 0.5. So I'm going to type this into the calculator, and it'll approximately be equal to the number of minutes it takes for this to happen. So we are looking good. Turn the calculator on here. Oh, we'll hang up the technology. So we got 15 multiplied times log, and we got 50 divided by 325, close the parentheses, and then divided by log of a half. So I chose log of 0.5 because it's faster to type in there, means the same thing. Uh-oh, error. Go to. What did I do wrong? I forgot to close the parenthesis right there. Second insert parenthesis. There we go. 40.5 minutes. So I didn't close the parenthesis there. Actually, I added too many parentheses, and I needed to close that one. So it's 40.5 minutes. I do all my videos in one take, so no apologies here. I'm just going along doing some math problems. All right. Our exponential growth decay formula is y equals ab to the x. So suppose a population is decreasing at 4%. There's 143 of them, and they're dropping down to 30. So we want to figure out how long that takes to happen. So anytime you could pause the video and read the question faster, I'm just kind of hitting the highlights of it. So 30 is our final amount. Our starting amount is 143. Start, stop, start, stop. And we're going down 4%. If I'm going down 4%, that means I'm keeping 96%. So I'm losing 90, or I'm keeping 96. I'm losing 4 pennies per each dollar. If you think about this as a dollar, I'm losing 4 cents to the x power. All right, divide the 143 over, just like we did on the last problem. This one solves out a little bit easier. So it's 30 over 143. As a fraction, I don't want to change that into a decimal because it'd be an awfully yucky decimal. And 0.96 to the x power. Okay, I'm going to take the log of each side. That's going to bring the x down to the front. So I get log of the fraction 30 over 143. And that's equal to x log of 0.96. There's multiplication in between here, so I'm going to divide over the log to do the opposite of the multiplication. That cancels out. That's the answer. Now I'm going to go a second time and type this into the calculator, see if I can do better this time. Log of 30 divided by 143. So see, I didn't put the extra parenthesis there. That'll help. And then divided by log of 0.96, because I'm losing 4%. So 38.3 years. That's equal to x. So that's how many years it's going to take before the species goes from 143 down to 30. This is minutes, this is years. So that x keeps changing all the time. Drink of water time. Okay, protactinium 234M. I like to say that. That's what we're dealing with here. This is a double problem. We have to figure out the rate of decay, and then we have to figure out how long it takes to get from a 10 milligram sample to a 2 milligram sample. So protactinium 234 is a radioactive isotope. It has extra neutrons, and it's going to change into regular protactinium. The half-life is only 1.17 minutes, so a very short half-life, and we want to figure out B first. So I start off with Y equals A, B to the X. My starting amount is a 10 milligram sample, and it's going to decay to 5. So that's the half-life, going from 10 to 5. So half of it's gone. I don't know the rate of decay. I have to solve for that first, and it takes 1.17 minutes. We're going to divide the 0.5 or the half, divide the 10 over, which will make it be a half or 0.5, and then B to the 1.17 power. We have to do the opposite power. So I'm going to take each side to the power of 1 over 1.17. So the reciprocal exponent always solves. So if it's b squared, you do the 1/2 power, which means square root. If it's b cubed, we do the 1/3 power, which means cube root. So here it's the 1.17 power, so I do the opposite power to each side, 1 over 1.17. So that gets typed into the calculator. B is approximately equal to 0.553. So that's the B. So I typed this into the calculator, 0.5 to the power of 1 over 1.17. And then hit enter, boom, there's your answer. So now I'm going to figure out how long it takes to go from a 10 milligram sample to a 2 milligram sample. So start, stop. And my rate of decay is 0.553. This is rounded, of course, to the I don't know power, because we're trying to figure out how long it takes to go from 10 to 2. Now I don't know the time. There's my decay rate, which is really close to 50%. So it's like 44.7% decrease every time. So that's pretty fast. So divide the 10 over. That would be 0.2 is equal to 0.553 to the x. Take the log of each side, because I'm solving, bring that exponent down to the front. And I get log of 0.2 is equal to x log 0.533. There's multiplication here, so that means the log gets divided over. So I'm dividing by log 0.533. That cancels out, and we get x is equal to, you type that into the calculator, log of 0.2 divided by log of 0.533, and the answer would be 2.717 minutes. There. Minutes. My minutes is kind of messed up there. That's kind of the idea with this, is we are dividing to get the 2/10. We take the log of each side, which brings the cookie jar down from the top of the refrigerator, right? See, the x is up there high. It's like on top of a a refrigerator, and it's like a little cookie jar, and you got to bring it down so you can see what's inside of it, if there's any good cookies in there. So we use log to do that. It's the opposite of exponential, bringing the x down to the front. All right, next problem. If you've watched Finding Nemo, we know that it's really deep and dark underwater. So this is A. As you go down farther and farther, you lose light at this rate. So you're losing 2.5% for every foot that you go down. So x is the number of feet, you're losing 2.5%. You start off with 20% and you go down. So output is the number of the percentage of light. So find the percentage of light for 50 feet down. So you put in a 50 for x. So x is the feet, there's your decay rate, 20, and then your output is a percentage. You just type this into the calculator, you get 5.64%. B, now we want to know how much there is at 370 feet down, so it's just the same problem. Type this into the calculator, you should get 0.0017%. Alright, that was chocolate from my snack earlier, right there, so that's chocolate. I had a little snack, a little energy boost to get me through the video. Okay, this is a double problem as well, and this one's a double problem as well, the one underneath. So phosphorus 32, we have to calculate out what B is first because we need to figure out how much is left after 84 days. So we start off with y is equal to a b to the x. Our sample size is 50 milligrams. So 50 milligrams is changing to half, 25. B is what we don't know. And it takes 14.3 days for that to happen. So we're going to solve for B just like in the other problems. We divide the 50 over. That's going to give us a half. B to the 14.3. So we're going to do the opposite power here, 1 over 14.3. And then 1 over 14.3. Alright, so this gets typed into the calculator. B is approximately equal to this half right here. So it's 0.5 to the power of 1 divided by 14.3. So 0.95, I think I went 27, 95.27. So 95.27. All right, so that's an approximation. Now we need to know how much is left after 84 days. So we have y is equal to, you're starting off with 50. My decay rate is 0.9527 to the power of 84. So how much is left after 84 times? You lose about 5%. Okay, so it's 50, this. We just type this into the calculator and you get y is equal to 0.8525 milligrams. So I type that in just like up here, type this in, get an answer, type this in. But we couldn't do the problem until we knew the growth rate. So to find the growth rate, you have a starting amount and it cuts in half for so much time. The reciprocal exponent solves for B. That's basically what it is. This problem here is iodine 131, and what are we doing with it? Oh, we got to calculate B again. So here we go. We have 200 milligram sample, so we have y is equal to a b to the x. So we have a 200 milligram sample, and that's going to 100 milligrams. And we know the half-life for this iodine, which is used to fix water pipe leaks, is 8.14 days. So my answer is going to be the number of days now. No, it says find the amount remaining after 72 days, so it's going to be the number of milligrams again. So divide the 200 over, I get a half again because it's the half-life. I'm going to do the opposite exponent, which is 1 over 8.14. 8.14. So that gets typed into the calculator. So these cancel out. You get B is approximately equal to 0.5 to the power of 1 over 814, which gives me 0.9184. All right, now I can use that just like on the last problem. We get 200 and we get 0.9184. to the x power, and that's, we want to know the amount after 72 days. So we know that this many days, it cuts it in half. So what's going to be left? Well, it's a lot more days, so it's going to be cut way more than half. There's going to be hardly anything left. So you type this into the calculator, you get 0.4349 milligrams. And again, units are important. So we've had milligrams for units, we've had percentages for units. Here we had minutes, years, minutes. Okay, last page, 2 problems. Okay, this is one where we're going to do the half-life. Carbon-14 is used to measure things that are really old, has a really super long half-life, 5,730 years. All right, so we start off with y is equal to a b to the x power. We have a 24 milligram sample. 24 milligrams is a double problem. So 24 milligrams is going to change to 12. And b we don't know, but it's going to take 5,730 years to do this. So that's my exponent. That's a giant exponent. So we divide this over. 0.2 is equal to b to the 5,730. Now, the opposite power of this would be the root of this. Oh my gosh, it's not square root, cube root, fourth root. The root is the 5,730th power, 1 over that. So you're going to do that over here, 1 over 5,730. All right, let's type this one into the calculator together. So we want to know the half-life, so half to the power of 1 divided by 5, or we want to know the rate of decay on this half-life, 5,730. Now, if I round this to 2 decimal places, the answer is going to be 1, and that's not going to make anything decay. So for this one, I'm going to keep 6 decimal places because the 0 there is kind of nice to work with. So b is approximately equal to 0.999879. All right, now we're going to figure out how much is left after 30 millennia, which is 30,000 years. So we have y is equal to 24. There's a 24 milligram sample. The decay rate is 0.999879 to the power of 30,000. And that's probably the largest exponent you've ever seen before, a 30,000 power. So, you know, like x to the first is a line, x to the second power is a parabola. We have we have the 30th power here. So you type this into the calculator, and how much is left of the 24 milligrams? Approximately 6.637 milligrams. All right. The next one, number 10, is about farmers. We have nt, so that would be like the number of farms is a function of time. T is time. And there's your starting amount. Now, that doesn't mean there's 119 farms in Iowa. It means there's 119,000 farms. And we want to figure out how long it takes to become 80,000 farms because they're decaying. So it's 119,000 farms, and we want to know when it hits 80,000 farms. The decay rate is 0.987 to the t power. So we're going to solve for t. So this is like problems that we've done before. We have to solve for t. Divide over the 1.19. Not 1.19, 119. I need to stop doing these videos. So it's 80 over 119 is equal to 0.987 to the t power. I have to get the t down to the front. So how do we get the cookie jar off the top of the refrigerator? We use a log. You can stand on the log, or you can throw a log at it, or whatever you want to do. So the t comes down to the front. So I have log of 80 over 119 is equal to t log of 0.987. Now I'm going to do the opposite here. I have t times this log. That's a number. So the log gets divided over 0.987. And I'm dividing the log away here, because you do the opposite always on each side of the equation. So those cancel out. And you got to type this into the calculator successfully. So let's type it in together. This is the last one. Log of 80 divided by 119, and those are in thousands, so the zeros all cancel out. It makes sense. divided by log, and then we got 0.987. So 30 years, 30.35 years. So 30.35 years is what t is approximately equal to. So in 30 years, they would be down that many. So this is 1980, and then 30 years past 1980 would be 2010. So supposedly that's where it would be down to. And I wouldn't be surprised that that's what's happened over time. Consolidation, people retiring, not wanting to farm anymore, et cetera, et cetera.